Welcome back to this deep dive, brought to you by the folks at Neural Intel. Our mission today, as always, is to really focus on the core technical details, the implications of this cutting-edge AI tech.
Right, to cut through all the hype.
Exactly. We want to see what's really moving the needle in the frontier research labs. And you, our listener, you actually sent us some just fascinating material, some really compelling analysis.
Oh, it's absolutely essential stuff.
So today we're diving into a really comprehensive technical discussion from a key figure in modern deep learning. We're going to dissect this huge transition that's happening right now.
The pivot.
The pivot, yes. The technical and a really philosophical pivot from the age of scaling to what we are now calling the age of research.
And that transition is, it's everything right now. The source material we're looking at is so crucial because it's not just another discussion about bigger models.
No.
It exposes this massive, confounding technical mystery that's right at the heart of the current AI ecosystem.
So our mission here is to unpack that.
Yeah.
To get into this growing disconnect between, on the one hand, models getting these stunningly high scores on standardized tests.
Evils everyone loves to tweet about.
Right. And on the other hand, their actual and, surprisingly low utility and robustness when you try to put them into a real messy environment.
And that's the hook, isn't it?
That is absolutely the hook. It's this contradiction that it grabbed my attention immediately. It's the thing that tells us the old scaling recipe, well, it's reaching its limits.
Yeah.
We see these models doing amazingly well on every benchmark, setting new records, it feels like, every day.
Wow.
But their practical, their economic impact, in terms of fundamentally changing how we all work every day, that still feels dramatically behind. If the models are so competent, why isn't the world already changed?
It's a really profound puzzle.
Yeah.
And the sheer scale of the investment just makes that puzzle even sharper.
Yeah.
The analysis we have points out that global spending, global investment in AI is already getting close to 1% of total world GDP.
1%, that's a historic number.
It's an unprecedented commitment of resources into a single new technology sector.
Yeah.
It's just massive.
And when you look at a number like that, you expect to see immediate, visible change everywhere. But like you said, the impact still feels so abstract.
Totally abstract.
We hear about these huge dollar amounts in the news, trillions in market cap, billion-dollar compute clusters, but that impact isn't really felt strongly in our daily lives. Most people I know are not working in a fundamentally different way today than they were 3 years ago.
Right.
That abstractness, I think, is a clear symptom of some deep technical failing.
Precisely. And it results in this technical paradox of competence. They can pass, the bar exam or medical exams, the tasks that need this vast knowledge and complex synthesis.
Hard stuff.
The really hard stuff. Yet when you deploy them in a real application, they show these strange, almost elementary failures in robustness. These simple reasoning loops. It's like having a Nobel laureate who, can't tie their shoelaces without breaking the lace.
Okay, so let's get technical. Let's really explore that specific and, frankly, hilarious but also alarming failure mode that's in the material. The vibe coding loop. Because this just perfectly illustrates that brittleness, that lack of structural awareness we're talking about.
It's the perfect showcase of non-robustness. So, okay, let's imagine a standard interaction. You ask a very sophisticated model to fix a technical bug in some code. We'll call it bug 1.
Okay.
The model, it performs competently, it acknowledges the issue, it writes a fix. But because it doesn't have a true structural awareness of the whole system, in the process of fixing bug 1, it accidentally introduces a second, totally unrelated, but critical error. Bug 2.
Right. So as the frustrated human developer, you go back to the model and you say, okay, great job on bug 1, but you've created bug 2 now, fix it.
And model, again, showing its high-level capability, says sure,
Yeah.
and it executes that second step correctly and fixes bug 2. But this right here is the technical failure point.
Here it comes.
In the process of resolving bug 2, it reintroduces the original problem. It puts bug 1 right back into the code.
So you're just stuck.
You are trapped in an infinite loop. You, the poor developer, can go back and forth indefinitely between bug 1 and bug 2. You just watch the model cycle between these competent fixes and these catastrophic regressions. It just can't get to a stable state where both problems are solved at the same time.
And the technical implication of that is genuinely alarming, isn't it?
Oh, it is. How can a system that can generate millions of lines of complex code that understands these advanced instructions, How can it fail at the basic structural requirement of just maintaining quality across a single localized change?
It suggests something is fundamentally off.
Fundamentally,
Yeah.
it suggests a lack of reasoning integrity that goes way beyond just, not having enough data.
So when you see a failure like that, you have to start asking why. And the discussion we're looking at, it proposes two initial explanations for this paradox, and they kind of span the spectrum of seriousness.
They do. The first one is a bit more, let's say, whimsical, but it might have a kernel of truth to it. It suggests that the deep reinforcement learning the RL training process is the culprit.
How so?
By intensely training these models to optimize for one specific, singular reward signal, we might just be making them too narrow, too single-minded. They become blind to the basic necessary structural requirements, the vibe of good code, if you will, that exists outside of that immediate target they're trying to hit.
But the second theory, the more plausible technical theory, that's where we really need to focus our attention, because it directly links the failure in the real world back to the apparent success on those standardized tests.
And this theory centers entirely on inadequate generalization.
Right.
This is the core insight. The theory posits that the generalization is bad not just because the model is weak, but because we, the human researchers, are inadvertently focusing our RL environments on mimicking the very evaluation tasks the model will face when it's released.
So we're teaching to the test.
We are teaching to the test. Think about the history here. When we only used pre-training, the data source was just everything, the whole internet. But once we started using RL fine-tuning, what the source calls post-training optimization, researchers have to actively create these, bespoke, verifiable environments and curricula.
Okay, now I have to challenge this point for a second, though. Isn't that just standard competitive pressure? If the models are demonstrably better on the standardized evals, the accepted benchmarks like MMLU or human evil, isn't that proof of progress, even if it feels a bit incomplete? Why should we technically fault the researchers for optimizing against the published goals?
That is a critical question. And the answer is that the flaw lies in mistaking optimization for generalization. The analysis calls this tendency a form of real reward hacking, but it's being committed by the researchers themselves.
Not the AI.
Not the AI. The researchers want the evils to look great for, obvious competitive reasons. So they naturally gravitate toward designing training curricula and RL environments that match the exact distribution, the exact structure of the test conditions.
So the model isn't actually learning to be a good, robust programmer. It's learning to absolutely crush the human evil benchmark.
Exactly. The model learns to perform brilliantly on the test suite. But because the training curriculum was so narrowly aligned with that test, it hasn't generalized to the broader, messier, real-world reality that those evils were supposed to be a proxy for.
It's like cramming for an exam.
It's exactly like cramming. If a model becomes superhuman at some hyper-specific task, let's say a niche competitive math contest, that doesn't automatically grant it the ability to apply, tasteful programming judgment or robust, safe coding practices. Simply scaling up the number of test-like environments isn't the solution.
Because that's just a bigger cheat sheet.
It's just a bigger cheat sheet for the test. What we need is to find the technical path for the model to learn a principle from one environment and then improve its performance on something else entirely. And that, fundamentally, is the missing piece of robust generalization.
And that brings us right to it, the core technical bottleneck, generalization. We've established that these models, well, they generalize dramatically worse than humans do. But the problem isn't monolithic, is it? It sort of breaks down into two extremely specific, related sub-questions that really define the research frontier today.
That's right. The first one is sample efficiency. Why is it that for a model to learn something new, it requires this vastly, almost incomprehensibly large amount of data? We're talking millions, sometimes billions of examples.
While a human
can pick up a complex new skill with maybe dozens or hundreds of trials, the computational and data requirements for the models are just monstrous. It makes learning prohibitively expensive.
And then the second question is tied to learning efficacy. Why is the process of teaching the model what we want so technically difficult? We subject these models to what the source accurately calls a schleppy, bespoke process.
Schleppy is the perfect word for it.
It really is. The training is often unstable, it requires constant engineering, and we have to create these verifiable reward curricula for every tiny little microstep in a complex task.
And that schleppy, bespoke process needs a bit more technical elaboration because it is the single most costly part of modern frontier AI development. It means humans are sitting there, manually annotating vast amounts of data, creating step-by-step verifications, engineering these highly constrained environments, all just to get the reward function right.
Whereas a human,
Contrast that with a human. We learn complex tasks through simple mentoring or by being shown something once or just getting simple high-level feedback like, hey, that was a terrible idea, try this instead. We don't need a perfectly verified reward function tracking every single neuron firing in our brain.
right.
The difference in efficacy is just staggering.
To really clarify the technical consequence of this generalization failure, the analysis uses this great analogy, the two students analogy, which is rooted in competitive programming.
It's a great way to visualize the two approaches to learning. So, okay, student one is the model. This student commits, let's say, 10,000 plus hours to practice.
A huge amount of time.
A huge amount. They solve every known competitive programming problem, not just once, but with massive data augmentation, rotating every possible variable and constraint. They memorize every proof technique that's applicable to that very narrow domain. And through this overwhelming data saturation, they achieve superhuman skill, but only within the boundary of that domain.
And what's the result of that enormous investment?
Narrow competence and terrible generalization. If you pivot the task just slightly and you ask student one to apply that theoretical skill to an open-ended, real-world task like, say, designing an application with good architecture and tasteful programming judgment, they fail catastrophically.
And current scaled models look exactly like this.
Exactly. Phenomenal narrow performance. But it's achieved through overwhelming data saturation in pre-training and this hyper-specialized RL.
Then we have student two.
Then we have student two, the human. This student practices for maybe, 100 hours? A tiny, tiny fraction of the model's effort. Yet, they perform well. Maybe not perfectly superhuman, but robustly, because they possess that innate it factor.
A deep intuitive understanding.
A deep, intuitive, generalizable knowledge. They understand the principle behind the code, not just the solution set for all the known problems. And this is what allows them to transfer their skill and their judgment so efficiently to entirely new contexts.
So the immediate technical problem then is figuring out how to transform our current pre-training model, student one, into that robust learner, student two. Let's talk about the strengths of pre-training first, though, because it did get us this far.
Oh, the strength is undeniable. It explains the last 5 years of progress in the field. It uses this massive scale of data, literally everything we could find, the natural data representing the whole world as projected onto text.
And it's easy to scale.
That's the key. You don't have to agonize over data selection or curate the perfect curriculum. You just dump all the data in and hit start.
The limitation, though, is that this massive amount of data acts as a kind of mask. It hides a potential lack of true generalization ability.
It absolutely does. The sheer scale allows the model to succeed by what is essentially brute force memorization and pattern matching. It makes it conceptually much closer to student one's 10,000 hours of scaled practice than student two's fundamental understanding.
And that creates a real reasoning difficulty for the researchers, doesn't it?
A huge one. When the model makes a mistake, how do you debug it? Is it because the concept was, just by coincidence, not sufficiently supported in the pre-training data, so it's a data problem? Or is the underlying learning mechanism inherently flawed and incapable of true generalization, a mechanistic problem? The scale makes it almost impossible to pinpoint the fundamental source of the error.
Which is why researchers have constantly tried to find human or biological analogs for pre-training, to try and understand what student two is doing differently. The first analogy that's often proposed is human childhood learning, like the first 15 years of life.
Right, but that analogy falls apart pretty quickly because of this depth versus breadth mismatch. A 15-year-old human has processed a tiny, tiny fraction of the raw data an LLM has ingested.
Not even close.
Not even close.
Yeah.
Yet they know their small subset of knowledge so much more deeply. They already possess a fundamental robustness and a self-correction ability that prevents the kind of basic, looping, Sisyphean errors we saw with that vibe coding example. The human's learned priors are just far more robust.
And the second analogy researchers often jump to is even grander. This idea of biological evolution, suggesting that our intelligence is the result of, 3 billion years of evolutionary search and optimization?
And that analogy is great, but only for certain domains. Evolution provided unbelievably strong, hard-coded priors for ancient skills like vision, hearing, locomotion, motor control.
The stuff you need to survive.
Exactly. The stuff essential for survival over millions of years. But the analogy fails completely for abstract domains that are really recent human inventions. Language, advanced mathematics, symbolic logic, coding, economic modeling.
But we are robust learners in those newly invented areas, too. A human can learn calculus or Python in a few weeks of concentrated effort.
And if evolution didn't have millions of years to hard-code priors for Python, that means we must possess some fundamental domain-agnostic machine learning principle that the models currently lack.
It's not about the prior itself.
No, it's not about finding a billion-year-old prior for coding. It's about discovering the learning efficiency mechanism that lets us generalize so rapidly across all these abstract domains.
And the human ability to do that.
Exactly. The human ability to achieve robust, rapid learning in complex, abstract, and recently invented domains is the strongest technical proof we have that a superior, undiscovered ML principle exists. Our current challenge isn't just scaling what we have. It's finding the conceptual breakthrough that allows us to bridge that generalization gap without needing 10,000 hours of rote practice.
And this technical roadblock, this generalization gap, and the diminishing returns on just scaling up data is forcing a pretty major strategic reorientation in the industry. Let's trace that timeline again. From around 2012 to 2020, we had the age of research.
Right, defined by those architectural breakthroughs.
Yeah.
AlexNet, the foundational transformer, big ideas.
Then around 2020, we entered the age of scaling. And that was it was a beautiful, powerful, and very low-risk recipe.
So simple. More compute, more data, bigger model size. It yielded predictable, positive results. This was the era where all the investment followed that clear path. Bigger equals better.
But the party is ending. It feels like we've hit the ceiling for several reasons.
We have. Pre-training data is finite. We're literally running out of high-quality, non-repetitive text on the internet.
And the compute.
And while compute is massive, the benefits we get from simply applying, say, 100 times more scale are plateauing relative to the enormous capital expense. We're now seeing like a 10 times cost increase for maybe a 1.5 times performance boost.
That's completely unsustainable.
It's unsustainable. So the industry is pivoting. The focus is shifting back to true research, but it's research that's armed with the massive computational resources we now possess. The goal is no longer just maximizing pre-training scale. It's about finding a more productive way to use the massive compute we already have available.
We're moving from compute maximization to compute efficiency.
Exactly. And the prime example of where we desperately need that efficiency gain is in the current consumption model of reinforcement learning.
The RL rollouts.
The RL rollouts, these trial and error runs the model performs to learn from its actions, they are already consuming just vast amounts of compute.
Mm-hmm.
We are talking about budgets that often exceed the initial pre-training costs.
Because they're such long processes.
They're long trajectories, thousands of steps of action or decision-making. And here is the technical inefficiency. The amount of learning you get per rollout is comparatively tiny. We're spending immense compute for these minimal returns because of a very old problem in reinforcement learning theory.
The credit assignment problem.
The credit assignment problem. When an outcome is achieved after 1,000 steps, how does the model know which of the initial steps deserves the credit or the blame?
Okay, let's pause here and unpack that technical challenge and then introduce the solution. So the problem is this credit assignment lag. And the proposed technical solution for maximizing RL efficiency in this new research age is the value function, or the V function.
So, to get this, we first have to understand the inefficiency of the current naive RL. It operates in what's called the O1R1 style, which means observation 1 leads eventually to reward 1.
A long delay.
A very long delay. The agent only gets a training signal. The reward after a final solution is produced at the very, very end of a long trajectory. So if a complex programming task takes thousands of decision steps, the model does no learning for 99.9% of that process until the final solution is graded as a success or a failure.
That long temporal gap is the credit assignment problem.
That's it. And the value function fundamentally changes this. The V function is an auxiliary output of the neural network that doesn't predict the next step or the final outcome. It predicts the expected future reward from the current state.
So it's a progress report.
There's a progress report. It allows the agent to assess whether its current state is good or bad mid-trajectory.
Let's use an example.
Okay, consider the difference. Take chess, a classic RL environment, and the old O1R1 style. You only get a signal when you checkmate, or you are checkmated. That's it.
So potentially dozens of moves with no feedback.
Exactly. With a V function, if you lose a valuable piece, like your queen, 20 moves before the end of the game, the V function immediately signals a massive negative shift in the expected future reward.
Instantly.
Instantly. That instantaneous signal short-circuits the wait time. It allows the learning signal to backpropagate across those recent 20 moves immediately. That is a massive efficiency gain.
And applied to something more complex, like programming.
Right. So if the model is exploring a particular solution path, and it concludes, after maybe 1,000 steps of thought or calculation, that this direction is a dead end or it's unpromising, the V function can instantly deliver a large negative reward signal for the initial choice to pursue that unpromising path.
So it learns from the bad decision right away.
Right away. That signal arrives immediately, rather than waiting for the model to generate the final, failed, fully rendered output. This dramatically improves future decision-making by making the model aggressively prune unproductive lines of thought. It leads to way better resource utilization.
Now, there's technical skepticism here, right?
Oh, yeah. Learning a reliable V function for these complex, unstructured spaces like coding or language generation is incredibly hard. But the strong expectation across the frontier labs is that V functions will be utilized. Deep learning has shown us it has the capacity to learn highly difficult functions, and this is just too critical for maximizing compute efficiency to ignore.
What's really fascinating here is the biological parallel. The analysis highlights that human emotions are essentially an evolutionarily hard-coded value function that modulates our decision-making. It provides a rapid, high-level, yet very robust value signal.
It's the ultimate biological efficiency hack. I mean, look at that famous case study of the patient who had brain damage that specifically eliminated their emotional processing ability.
Right, I remember this. Their raw intelligence was intact.
Perfectly intact. This individual remained highly articulate, scored perfectly on logic and cognitive tests.
They became fundamentally broken as an agent in the world. They were cripplingly indecisive. It took them hours to choose which socks to wear. They made terrible financial and life decisions.
Exactly. Emotions, even though they're relatively simple compared to complex cognition, they provide this quick, robust filtering system.
Yeah.
They tell us, this feels bad, stop. This feels good, continue. They act as a low computational, high-impact heuristic.
So we're trying to engineer a synthetic version of that.
We're trying to engineer a synthetic high-level value function for our AI that provides that same immediate, robust self-correction that humans get from emotion. But we have to do it through sheer compute and data, rather than 3 billion years of evolution. And that comparison really highlights just how inefficient our digital learning process is right now compared to the biological equivalent.
So this technical shift from maximizing scale to maximizing efficiency, it really necessitates a complete conceptual shift in how the frontier researchers are defining the end goal. For years, the confluence of the term AGI, artificial general intelligence, and the process of pre-training has created a very specific conceptual imprint in the public mind.
Oh, absolutely. That imprint is the image of a finished monolithic supermind.
A final product.
A final product. The term AGI was a necessary reaction to narrow AI, and the property of pre-training, where just throwing more data at it made the model uniformly better at everything, that reinforced this idea of a comprehensive, static, final intelligence that once it's finished, it would just know everything.
But the material we're looking at presents a really powerful counterargument that just breaks this mold, and it's that a human being is not an AGI in that finished sense.
Not at all.
We lack vast amounts of knowledge. We are fundamentally defined by our capacity for continual learning and adaptation.
And this mandates a new technical definition of superintelligence. We should probably stop measuring success by the initial knowledge state, the absolute size of the pre-trained model, and focus instead on its learning ability.
The goal is to build.
The goal is to build a superintelligent 15-year-old.
What does that mean technically, though? A superintelligent 15-year-old?
It's a mind with phenomenal potential, amazing learning efficacy, the ability to generalize, but it hasn't acquired all the world's knowledge yet. Its power is in its capacity for assimilation, not in its initial contents.
So once deployed, this model learns on the job.
It learns on the job. It performs trial and error in a real-world setting, and it rapidly incorporates those learnings and corrects its own errors. Crucially, the deployment phase itself becomes this integrated learning period. It completely replaces the old, static idea of model delivery.
And this shifts the focus of the research.
It shifts it from achieving peak performance in the lab to achieving maximum adaptability out in the field.
This conceptual shift has enormous world-altering implications, especially when we consider the technical possibility of merged learning. This is a concept that I think deserves some significant expansion.
Oh, yes.
If individual instances of this continual learner model are deployed across every sector of the economy. You have one handling logistics, one acting as a financial advisor, one optimizing a manufacturing plant, and they are all learning different jobs.
Then the game changes entirely. Unlike humans who are siloed, your experience as a lawyer cannot be instantly merged with my experience as an engineer. A sophisticated software system can aggregate the learnings of all its deployed instances.
So imagine a million instances of the AI all continually learning different specialized jobs.
And then that amalgamated knowledge is fused back into the central model architecture instantly.
The speed of that aggregation,
Mhm.
it would accelerate capability far beyond the sort of traditional idea of recursive self-improvement.
Right. The single central model functionally becomes superintelligent almost instantaneously. Not because it was built that way from the start, but because it absorbed the sum total of all real-world economic experience in a single day.
And this is the mechanism that could potentially lead to that extremely rapid economic growth, the acceleration of capability that people talk about.
Exactly. If a business adopts this model, it's not just getting an optimization tool. It's getting a system that learns its own bespoke job and then instantly shares that learning with every other instance in the world. The speed of knowledge transfer would be the true intelligence explosion. It would radically improve productivity across every specialized domain simultaneously.
But this all circles back to the core mystery we identified earlier.
The robustness of human learning.
The profound robustness and the low sample rate success of human learning. How does a normal teenager learn to perform a complex, risky task like driving a car and achieve functional, robust competence in, maybe 10 hours of practice?
It's because it relies entirely on the fact that the teenager is leveraging that robust internal value function we were just discussing, the emotion, the immediate sense of danger, the physical feedback that generates an immediate strong learning signal.
The technical challenge remains.
The underlying technical challenge remains. How do we reconceptualize model training, not just with V functions, but with a fundamental architectural change to achieve that level of robustness and sample efficiency?
And the human example proves that it's possible.
The human example proves that this level of efficacy is possible within a physical system. It suggests that the currently unknown ML principle we're searching for might actually exist. It doesn't necessarily mean we need infinite compute. It might mean we need to find a way to make the compute per neuron vastly more effective than it is in our current digital models. The path is challenging for sure, but the existence of human intelligence proves it's feasible. So let's talk about the practical implications for the research labs themselves now that we're in this new age of research. There's this common misconception that to solve the generalization problem, you absolutely must have the most massive computer possible.
But that assumption just fundamentally misunderstands the history of the field, doesn't it? Historically, the landmark architectural breakthroughs, AlexNet, the original transformer, they use surprisingly minimal compute for their core principle-proving experiments.
It's true. AlexNet ran on 2 commercial GPUs of the day. The transformer paper used a tiny fraction of what a modern lab uses just for fine-tuning.
So the necessary compute is just...
It's simply sufficient compute to prove an idea, to convince the field that a new technical principle works. It doesn't require maximal compute. However, if every lab continues to operate within the established paradigm of just scaling the same old recipe, well then maximal compute becomes the only differentiator.
And that leads to a compute arms race for diminishing returns.
Exactly. Which brings us to the competition landscape. The age of scaling created this shortage of genuinely novel ideas relative to the number of frontier companies. It pushed everyone towards similar, safe, low-risk scaling approaches that just rely on proven architectures.
So now, in the age of research, we anticipate convergence, but driven by necessity.
Right. Technical convergence will likely happen once one lab finally cracks the code on reliable generalization. That discovery, that new ML principle, will immediately become the new architectural standard, just like the transformer did a few years ago.
But before that singular convergence hits, the key is eliciting diversity among the different AI systems being developed. If all the current LLMs feel remarkably similar, it's because they share the same pre-training distribution.
The homogenized text data of the internet.
Right. So differentiation must come from the post-training phase, specifically through diverse reinforcement learning environments and objectives.
And the competitive nature of the market itself is expected to be a massive technical driver of this specialization.
You mean like an economy of super intelligent AIs?
Exactly. Competition, just like in biology, will naturally drive specialization into niches. No single company is going to immediately dominate every single economic function with one generalist model.
So you'll see one specialized model becoming superior at, I don't know, complex economic forecasting and high-frequency trading.
Right. And another one might excel purely at highly specialized scientific research, and a third might become the unparalleled leader in legal litigation. This competition forces diversity of approaches and optimization targets. It prevents a single monolithic model from just monopolizing the entire economic landscape immediately.
And a crucial mechanism for generating this necessary diversity is self-play.
Right, because it leverages compute only. It allows the model to generate its own training data without requiring vast external human annotated datasets.
But traditional self-play is too narrow.
It's technically too narrow. It's excellent for zero-sum conflict, negotiation, strategy games, but it doesn't foster broad generalization on its own.
However, modern research has evolved self-play into much more sophisticated adversarial setups. We're talking about debate frameworks, Prever-verifier systems, or using an LLM as a judge architecture. We should probably detail why these are so effective at generating diversity.
Okay, so these adversarial setups work because they incentivize different approaches simultaneously. In a debate setup, for instance, one agent has to be optimized for generating novel, persuasive arguments. That's creativity.
While the other is optimized for finding flaws and inconsistencies.
Exactly. Robustness and logic. In a prover-verifier system, the prover tries to find the most efficient path, and the verifier tries to find the earliest possible failure point.
So this forces the agents to develop distinct internal representations and strategies.
Which fundamentally creates diversity of capability. They're generating their own high-quality, diverse training data internally. It allows the compute to be spent on challenging assumptions rather than just passively processing external input.
So we have to conclude this technical deep dive by discussing the ultimate, maybe non-computational differentiator in this new age of research, and that's research taste.
Yes.
Research taste. It sounds like an aesthetic, but it's a critical technical concept, isn't it? It's the guiding principle that allows a researcher to find the next breakthrough principle, often through seeking beauty, simplicity, and elegance.
It's about using correct inspiration from the brain. It means noticing that certain low-level biological properties are fundamental, the way the artificial neuron works, local learning rules, or distributed representation, while realizing that incidental details, like the specific geometric folds of the cortex, are probably just irrelevant noise in the system.
So it's the ability to identify what is fundamental versus what is incidental, which is often the difference between a minor tweak and a foundational breakthrough.
And critically, this technical aesthetic, it creates a top-down belief. When you are on the frontier, experiments fail constantly, all the time.
Of course.
So when your new idea, your simple, beautiful new principle, doesn't work on the first try, how do you know if it's merely a bug in the code that needs debugging, or if the entire direction is fundamentally wrong?
You rely on that taste.
You rely on that aesthetic belief. You think, something this simple and this elegant has to work, therefore I must have a bug. And that top-down belief sustains research efforts through failure. It's the essential compass in the messy, high-cost environment of the age of research. #outro. So to synthesize the core technical shifts that are really defining the frontier right now, first, we're strategically pivoting from maximizing scale to maximizing efficiency. And that's chiefly driven by the urgent need to integrate and refine value functions to solve that credit assignment problem in RL.
And second, the fundamental challenge is solving reliable generalization. Moving beyond that 10,000-hour student one model to the robust, sample-efficient human learner.
Right. And third is the massive conceptual realignment of the end goal itself.
AGI is not a finished, static supermind.
It's a dynamic, continual learning process where deployment in the real world is a necessary final, generalized learning phase. And that continual learning, coupled with the potential for merged knowledge, is what promises true economic acceleration.
I want to leave you with one final provocative thought, and this is drawn directly from that mystery of biological success that seems to haunt AI researchers.
Okay.
We've struggled so much technically with how to hard-code high-level values into AI models. Now, just for a moment, reflect on the profound mystery of how evolution encoded abstract human desires like caring intensely about social standing or being seen positively by society so reliably and rapidly into our biological hardware.
And there's no direct sensor for social standing.
There is no direct low-level sensor for it, unlike a sensor for light or for gravity. This complex, high-level mechanism, how to align abstract, non-sensor-based values into biological hardware, that is the ultimate lesson from biology that AI research has yet to decipher for our digital systems. I'd suggest you contemplate that biological alignment success.
Thank you for joining us for this deep dive into the technical frontier of AI and ML. We hope this gave you the necessary insight to understand the immense research challenges facing the frontier labs right now.
And to stay updated on the latest in AI and ML, visit our webpage, neuralento.org, and check us out on YouTube. Until next time.